Everything around us is moving. From tiny dust particles to massive planets. Motion is everywhere in nature.
Welcome to Grade 9 Science, where curiosity becomes discovery. Physics helps us understand motion, forces, energy, gravity, light, and the universe around us. Together, we will explore the laws that govern everything from tiny particles to giant galaxies. Like, comment, subscribe. Let's begin our exciting journey into the world of physics.
Introduction. Motion in nature. Everything in nature is in motion, from massive astronomical objects to subatomic particles. Dear students, understand this big idea first. In the whole universe, absolutely nothing is permanently still. Giant objects like stars, planets, and galaxies are moving, and at the same time, the tiniest things, atoms and the particles inside them, are also moving. So motion is not a special event, it is the normal state of everything around us. Understand this: rest and motion always depend on what you compare with. Examples of motion in nature include flitting butterflies, slithering snakes, and hopping hares. The textbook gives living examples so you can picture motion easily. A butterfly flutters, a snake slides, a hare hops. Each moves in its own pattern, but all are examples of bodies changing position with time. More examples: galloping horses, climbers' tendrils twining around a support, and closing of fly traps. Notice that motion can be fast, a galloping horse, or very slow, a plant tendril slowly curling, a fly trap closing. Speed does not decide whether something is in motion. Any change of position counts. Dancing dust particles in a sunbeam and smoke particles moving in air are also motions. Even motion you can barely see is real motion. Tiny dust and smoke particles keep moving randomly in the air. This tells us motion happens at every scale, big and small. Rising and falling of ocean tides and gathering clouds are examples of motion in nature. Here, the whole point is scale. Motion also happens on a huge, slow, natural level. Tides rising and falling, clouds gathering and drifting. Nature is full of motion of every size. To study a complex phenomenon, scientists first study it in idealized, simplified forms. This is the method of science, so remember it. Real motion is messy, so scientists first imagine a clean, simple version, ignoring small disturbances, solve that, and then slowly add back the complications. This is why we start with simple, straight-line motion. Understand, idealized means a simplified model, not something false. Simplified types of motion include linear, circular, and oscillatory motion. There are three basic simple motions you should know by name. Linear, along a straight line. Circular, round a circle. And oscillatory, to and fro, like a swing or pendulum. By heart, the three simple motions are linear, circular, oscillatory. This chapter focuses on linear motion, motion in a straight line, and uniform circular motion. Out of the three, this chapter deals mainly with two: motion in a straight line and uniform, steady-speed circular motion. Keep this scope in mind for your exam. Earlier grades covered physical quantities such as distance, time, and speed. The chapter assumes you already know distance, time, and speed from earlier classes. Revise them because everything new is built on top of these. This chapter introduces displacement, average velocity, and average acceleration. The three new, more precise quantities of this chapter are displacement, average velocity, and average acceleration. Learn these names now. The whole chapter revolves around them. By heart, the three new quantities are displacement, average velocity, and average acceleration. That completes portions 1 to 10. Keep practicing, and I'll see you in the next part.
Look around you. Everything in nature is moving.
Animals, vehicles, waves, clouds, and tiny particles are constantly in motion. Motion is one of the most important ideas in science. Let's discover how scientists describe motion around us. Let's understand the difference between distance traveled and displacement. The athlete covers a total path of 160 meters, but displacement only measures the shortest straight line change from start to finish. Distance depends on the entire path traveled, while displacements only on the starting and ending positions.
Motion can be described not only in words, but also with numbers, equations, and graphs. Understand the plan of the chapter. We will describe motion in 4 ways: words for definitions, numbers for values, equations for formulas, and graphs for pictures. Being able to move between these 4 is the real skill. 4.1. Motion in a straight line. When an object moves in a straight line, its motion is called linear motion. Definition to learn. Motion along a straight path is called linear motion. No curves, no turns, just a straight line. By heart. Linear motion is motion in a straight line. Linear motion can also be called motion in a straight line. Don't get confused in exams. Linear motion and motion in a straight line are 2 names for exactly the same thing. Linear motion is the simplest kind of motion. Because there is only one straight path and only 2 possible directions, linear motion is the easiest to analyze. That's why we study it first. Examples: children in a swimming race, a vertically falling ball, a car on a straight highway, a train on a straight track. Keep a few standard examples ready for answers. A swimmer in a straight lane, a ball falling straight down, a car on a straight road, a train on a straight track, all move in a straight line. To discuss the motion of an object, you first need to describe its position at various instants of time. This is the starting step of the whole subject. Before we can say how something moves, we must be able to say where it is at each moment. So, position comes first, and everything else is built from it. 4.1.1. Describing position. To describe an object's position, we first specify a fixed point as the reference point. To say where something is, you need a fixed point to measure from. This fixed point is called the reference point. Without it, saying it is 5 meters away is meaningless. 5 meters from what? By heart. The reference point is the fixed point from which position is measured. The distance and direction of the object with respect to the reference point at any instant describes its position. Carefully learn this. Position equals distance plus direction from the reference point. Both parts are needed, not just distance. Apart from distance, we also specify direction from the reference point to describe position. The textbook stresses direction again because students often forget it. Saying 5 meters away is incomplete. You must say 5 meters to the right or 5 meters to the left. If the position of an object relative to the reference point changes with time, the object is in motion. Definition of motion. If an object's position, measured from the reference point, keeps changing as time passes, we say it is in motion. By heart, change of position with time is motion.
An object is at rest if its position relative to the reference point does not change with time. Opposite case. If the position stays the same as time passes, the object is at rest. Rest and motion are always judged with respect to a reference point. Understand, the same object can be at rest for one observer and in motion for another.
To describe motion, we first need a fixed reference point. Scientists choose a fixed position called the origin or reference point. Now we can accurately describe where the athlete is located. Every measurement of position starts from a chosen reference point.
For an athlete running on a straight track, her starting point can be taken as the reference point. In the book's example, the runner's starting point is chosen as the reference point, the origin. We usually pick the start because it makes the numbers simple. The reference point marked on a straight line is called the origin, O. When we draw the straight line, like a number line, the reference point on it is called the origin and is labeled O. By heart, origin, O, is the reference point on the line. For an object moving in a straight line, it can move only in one of two directions, forward and backward. Understand the simplicity here. On a straight line, there are only two possible directions. This is exactly why straight line motion is easy to handle mathematically. Direction is represented by plus and minus signs. Instead of writing forward or backward every time, we use signs, plus for one direction and minus for the other. This sign system is very important later for velocity and acceleration. By heart, plus and minus signs stand for the two directions. Positions to the right of reference point O are generally taken as positive. The usual convention, the right side of O is the positive side. You may choose otherwise, but this is standard. Positions to the left of O are taken as negative. Correspondingly, the left side of O is the negative side. Once you fix these signs, you must not change them in the middle of a problem. Careful. Fix your plus and minus directions at the start and keep them the same throughout. 4.1.2 Distance traveled and displacement. Total distance traveled is the entire length of the path covered by an object. Definition: distance is the full length of the actual path traveled, following every twist and turn. It only asks, how much ground did you cover, not where you ended up. By heart, distance is the total length of the actual path. Example: an athlete goes O to A, 100 meters, then A to B, 60 meters, giving a total distance of 160 meters. To find distance, simply add all the path lengths. 100 meters plus 60 meters equals 160 meters. Even though she came back part way, every meter she moved is counted. The distance between starting and stopping positions can differ from the total distance traveled. Very important idea. How far you actually walked, the distance, can be very different from how far you ended up from the start, the displacement. This difference is the heart of this section.
Position is not just about distance. Direction is equally important. Positions on the right side of the origin are usually taken as positive. Positions on the left side of the origin are usually taken as negative. To describe an object's position accurately, we must know both its distance and direction from the reference point.
Displacement is the net change in the position of an object between two given instants of time. Definition to memorize: displacement is the straight line change in position from the starting point to the ending point, start to end. It ignores the path taken. By heart, displacement is the shortest straight line change in position from start to end with direction. A complete description of displacement requires both a direction and a numerical value with units. Since displacement is a vector, you must give both a number with unit and a direction. 40 meters in the positive direction is a complete answer. 40 meters alone is not. The numerical value with units of a physical quantity is called its magnitude. Learn this word. Magnitude means only the size, the number part with units leaving out direction. For example, the magnitude of a displacement of 40 meters north is just 40 meters. By heart, magnitude is the numerical size with units without direction. The magnitude of displacement is the distance between the object's positions at the two instants. The size of the displacement is simply the straight line gap between the start position and the end position. The direction of displacement is from the position at the first instant toward the position at the second instant. The direction of displacement always points from where you started to where you finished, from the first point toward the second point. To describe total distance traveled, only the numerical value with units is required. not direction. Distance is a scalar, so it needs only a number with a unit, no direction. This is the key difference from displacement. The SI unit for both distance and displacement is the meter. Both quantities are measured in meters. Remember, they share the same unit but differ in meaning. One is path length, the other is straight line change with direction. By heart, the SI unit of distance and displacement is the meter. Example: between t equals 0 seconds and t equals 16 seconds, the distance is 160 meters, but the displacement is 40 meters in the positive direction. This single example proves the whole point. Because the athlete turned back, the distance, 160 meters, and the displacement, 40 meters, come out different. Learn this example well. It is a favorite in exams. An instant of time is a single reading of a clock at a given point of time. An instant is one exact moment, a single tick like t equals 4 seconds. It has no duration. A time interval is the duration between two instants of time, two clock readings. A time interval is the gap between two moments. For example, from t equals 4 seconds to t equals 10 seconds is an interval of 6 seconds. Do not mix up instant, a point, with interval, a gap. Careful, an instant is one moment. An interval is the time between two moments.
Some objects move slowly, while others move incredibly fast. Scientists measure speed by comparing distance traveled with time taken. Average speed tells us how much distance an object covers every second. The greater the distance covered in the same time, the greater the speed.
Physical quantities specified by just a numerical value are called scalars. Scalars have size only, no direction. Examples: distance, speed, time, mass. By heart, a scalar has magnitude only, like distance, speed, and time. Physical quantities that require both direction and magnitude are called vectors. Vectors have both size and direction. Examples: displacement, velocity, acceleration. You'll study vectors deeply in higher grades. By heart, a vector has magnitude plus direction, like displacement, velocity, and acceleration. For straight-line motion, distance and magnitude of displacement are equal if the object moves in one direction without turning back. Special condition to remember: if the object moves in one direction only, never turning back, then distance equals the magnitude of displacement. The moment it turns back, they become different. The magnitude of displacement is always less than or equal to the total distance traveled. A golden rule: displacement can never be bigger than distance. At most, they are equal, when the motion is straight with no turning. Otherwise, displacement is smaller. By heart, the magnitude of displacement is less than or equal to distance always. 4.1.3 Average speed and average velocity. Average speed tells us how fast or slow an object moves. Average speed gives an overall measure of quickness for a whole journey. It does not care about direction or moment-to-moment changes. Average speed equals total distance traveled divided by the time interval. This is a key formula. Divide the total path length by the total time taken. By heart, average speed equals total distance divided by total time. Since distance has no direction, average speed also has only a numerical value and no direction. Because it is built from distance, a scalar, average speed is also a scalar, just a number, no direction. If an object travels equal distances in equal intervals of time, it is in uniform motion in a straight line. Definition: equal distance in every equal time slot is uniform motion. For example, 20 meters every second, second after second. By heart, uniform motion equals equal distances in equal time intervals. In uniform motion, the object moves at a constant speed. Uniform motion simply means the speed never changes, it stays constant.
If an object travels unequal distances in equal intervals of time, it is in non-uniform motion. Opposite case. Different distances in equal times is non-uniform motion. This means the speed is changing. By heart, non-uniform motion equals unequal distances in equal time intervals.
When an object covers equal distances in equal intervals of time, it is in uniform motion. The speed remains constant throughout the journey. But when distances change during equal time intervals, motion becomes non-uniform. Uniform motion means constant speed, while non-uniform motion means the speed is changing.
In non-uniform motion, the object moves with increasing speed, decreasing speed, or a combination. During non-uniform motion, the speed may rise, fall, or do both at different times. It is simply not steady. If distances traveled in successive equal intervals increase, the speed is increasing. A practical test. If each second the object covers a bigger distance than before, it is speeding up. The concept of speed dates back to ancient India, seen in the Idealised of the 5th century CE. This is a knowledge and heritage point. The idea that speed equals distance divided by time is very old and appears in Aryabhata's Idealised in the 5th century CE. Good for value-based and general knowledge answers. The Ganita Kaumudi of the 14th century CE contains a mathematical problem based on speed. Another heritage fact. The Indian text Ganita Kaumudi of the 14th century CE also contains a speed problem, showing India's long tradition in mathematics. Example 4.1. Two postmen, 210 yojanas apart, walk toward each other at 9 and 5 yojanas per day. A classic moving towards each other problem. When two bodies approach each other, their speeds add up because the gap closes faster. Combined, they cover 14 yojanas per day, so they meet after 210 divided by 14, which is 15 days. Method. Add the daily distances. 9 plus 5 equals 14. Then divide the total gap by it. 210 divided by 14 equals 15 days. Learn this trick for time to meet problems. By heart. Time to meet equals total gap divided the sum of the speeds. Speed tells how fast an object moves, but gives no information about direction. The limitation of speed. It can never tell you which way the object is going. To include direction, we need a new quantity, velocity. Average velocity describes how fast an object's position changes and in which direction. Velocity is speed with direction. It tells both how fast the position changes and in which direction. By heart. Velocity is speed with direction. It is a vector. Average velocity equals change in position, the displacement, divided by the time interval. Key formula. Divide displacement, not distance, by the time interval. By heart. Average velocity equals displacement divided by time. Average velocity is written as V average equals S over T. In symbols, V average equals S divided by T, where S is displacement and T is the time interval. Learn the symbols.
Welcome to Grade 9 Science, where curiosity becomes discovery. Physics helps us understand motion, forces, energy, gravity, light, and the universe around us. Together, we will explore the laws that govern everything from tiny particles to giant galaxies. Like, comment, subscribe. Let's begin our exciting journey into the world of physics. Look around you. Everything in nature is moving. Animals, vehicles, clouds, and even tiny particles are constantly in motion. Motion is one of the most important ideas in science. Let's discover how scientists describe motion around us.
Class 9 and 10 students. Don't worry, make science and social science easy with your CBSE teacher. Subscribe now, like, comment, and press the bell.